Okay, and I should start off saying that we actually rely on the program that Sean just talked about. We submitted a proposal like this in JWST cycle 3, and one of the complaints by the reviewers is that why didn't we try this with a sort of a cheaper to use telescope like Keck, and so now we have. Okay, so yeah, so I mean, some discussion about this before. So we've been talking about the free-floating planets now discovered with finite source effects. And here's this slide showing the Einstein gap with the 3 events detected by Ogle in blue. Some of those are also in the KMT sample. And so there's basically nothing between 10 microarc seconds and 30 microarc seconds. So what's that? I think I hit that. Okay.
Oh, okay.
Yeah. All right. Okay, so this is a point that Naoki mentioned, but actually fitting for the finite source effects is actually important even when you don't detect it. And in particular, there's limits on what the relative proper motions of stars are. We know a bit about this because we studied the motions of stars in our galaxy. And so so this is showing 3 or 4 of the events from this MOA 9-year sample. 2 of them have precise measurements of theta E. But then other ones have pretty tight constraints. This one, when you apply a galactic model here, you find that you have a pretty tight constraint on the relative proper motion. There's this sort of tail to very high proper motion stars, but it's low probability. And so there we have a pretty good constraint, and also for this one we have a reasonable constraint. Yeah, so Naoki also mentioned the importance of calculating the detection efficiency in these 2 parameters. But an important thing here is that this detection efficiency at very short durations it depends on what the free-floating planet mass function is. Okay, but if you're doing forward modeling, then you can calculate the detection efficiency for every model while you're doing the analysis. So you don't have to apply a prior that you're not certain of. You just do that forward calculation. It can be complicated if it can be time consuming if the detection efficiency for every event is sensitive to both parameters. But you see here, it's not really, and for events longer than 10 days, there's basically no dependence. Okay, and so another important thing is going to be discussed here before is that the ideal thing would be if you get, in addition to TE, theta E, is also to measure the microlensing parallax. And the crucial thing here is that the separation you need to measure the parallax of these very short duration events is about 1/100th of an AU, which is the distance between the Earth and L2. And since Roman is going to be observing mostly when the separation from the Earth is perpendicular to the line of sight, this gives us a reasonable baseline between the telescopes in the vicinity of the Earth and or telescopes with a separation from Roman of about 1% of an AU. Here's a demonstration from a telescope at L2 and the ground, showing a binary event with different times of Costa crossing seen from Gaia and from the ground. And this is the 4-hour difference in times. So it's demonstrated already, and we're going to hear more about this from a couple talks. later in the meeting. Okay, so here's a slide showing positions on the color magnitude diagrams of a lot of the free-floating planet candidates, although it's the ones with finite source measurements. And so you see most of the ones, so the ones in black are free-floating planets, and the ones in blue, and then this diamond, this one is the ogle low mass free-floating planet candidate. And so most of them have been found with giant sources. Okay, and so yeah, so we talked about this already. How do we know if they're unbound or in wide orbits? And so the microlensing signals are expected. You can miss a microlensing signal of a host star with a separation as small as around 10 AU. For some events with smaller angular source sizes, you can actually get tighter constraints if they're moderately high magnification. And as you mentioned, in order to, we can search for candidate host stars in high angular resolution imaging, and then subsequent follow-up images can determine whether it's consistent or not with wide separation host star. Okay, so I want to talk a little bit about how we do these measurements. Sean already talked about that a little bit, but we have a lot of history doing this for not free-floating planets, but planets that are found orbiting stars. And sometimes we don't detect any stars. One case, we can rule out everything, but we can use microlensing parallax to rule out brown dwarfs, neutron stars, and black holes, and use a lack of detection to rule out main sequence stars. The only thing left is a white dwarf, and Aparna is going to talk about that later. But here's a couple of events that we've observed multiple times, and we can measure the separation of the stars that moves away. Here's one, and here's one using both late-time Keck images and earlier HST images. And so we can look at our results from these types of measurements. And here's a function showing our delta magnitude, the contrast, ranging from almost equal brightness stars down here to some with about 4 magnitudes of difference. And at 4 magnitudes, we're running into pretty close to a hard limit with Keck, because the Keck background compared to from space is pretty high in infrared. Also, the AO images, that Strel ratio isn't getting close to 1, and that's partly because a lot of light gets scattered out that pretty far away from the star, and that adds to the background. And so so roughly around 4 magnitudes is likely to be a limit with adaptive optic systems like or on Keck. Possibly future adaptive optic systems could be better. All right, so here's the event that Sean just talked about. And at 18 milliarc seconds, I looked up our Markov chain observations here, and we actually we don't have any simulations, any models of the microlensing event that are consistent with a separation smaller than about 50 milliarc seconds. That's between the planet and the source. And so as Sean mentioned, it's possible that a wide orbit host star with a wide orbit could be, trailing behind and just be at 18 milliarc seconds now. But if that's the case, it should still be moving at the same speed. So another epoch of observations, we should see it. We should see motion that's consistent with the measurement from the paper. I should say that since it's not entirely clear which one of those would be the host star, I think the favored solution is the brighter one, but the fainter one can't be ruled out. However, We also, we've done a preliminary analysis, I'm not ready for publishing this yet, but preliminary analysis at the upper limit of a host star, if we assume that neither of these is a host star, the upper limit of the mass, if it's in the bulge, is a bit over 4/10 of a solar mass. Okay, so even the follow-up observations exclude that. We're not be able to rule out all main sequence host stars. A low mass host star could possibly still be there. You wouldn't be able to see it with that. Yeah, so a more sensitive instrument would be nice, and it turned out that there's one that you just launched a couple years ago, and that's JWST. So it's much fainter background. JWST has a much better angular resolution at a wavelength longer than HST at a wavelength longer than a micron, sometimes the collecting area of HST. It does not travel in and out of Earth shadow every 45 minutes. And this means that the PSFs are much more stable. It's not designed for high contrast imaging in crowded fields. However, that doesn't mean that it won't do a good job. All right, so this is a slide now showing, this is data from observations of the Large Magellanic Cloud, which conveniently is at the south ecliptic pole, and so it can be observed by JWST at any time. The sun is never in the way. So here's observations at different pass bands. You can see there's a lot of scatter out here, whereas this one at 2 microns has a pretty regular pattern. There's features in the telescope design that give you these sort of regular pattern. But anyway, the point here is that the PSF models that Jay Anderson is building actually at this wavelength, they're matching the Poisson noise prediction, meaning that as far as they're about as perfect as they can be. There's a little bit more noise at the shorter wavelengths, but we hope to be able to remove that as well. Okay, so no one's ever done observations, at least in data that's public, that tries to do the kind of precision, contrast ratio measurements without any kind of coronagraph. And so one of the things we need to do is basically have many dither patterns. And so our proposal has between 36 and 54 dithers. So that's basically not quite 10 times better than previous attempts. We also need to take images on at least a full detector. So we have lots of stars of similar color to the target to build the PSF model. We need precise color information. One of the reasons is that we want to build a good PSF model. The filters I just showed on the previous page are all wide filters. That means that you can tell, different stars, different colors will have different shaped PSFs, particularly when in most of those wavelengths, it's undersampled. So you really want to be building PSFs from stars of the same color. Also, if you could, it's good to use not those filters I showed, but the narrower ones. There's medium filters and then very narrow filters. And also, by going to the narrower filters, you can still take images of bright stars with a full chip field without having to stop that field down to make the reads faster. And so by using the narrow band filters, we're looking at bright targets, you address 2 issues. One is that you can use this big array to get lots of PSF stars, but also reducing the range in color means that even stars of different color, if you use a narrow filter, they still look the same because only a small part of the spectrum is coming through. Okay, so here's a comparison to the best thing we could find in data that's currently available. So this is showing, so stellar image, this is a catalog PSF from Jay Anderson's method. Then he perturbs it makes the PSF somewhat better, but still a bit of noise. Then he adds a 6 magnitude fainter star, and then the faint star only is the PSF model. And so this is pretty well at getting the separations, but there's a bit more noise in the photometry, but still over most of this range, it gets better and better than 20% error. Okay. So the worst case is at the galactic center. The stars a lot of different colors. So there's foreground stars that are pretty blue, and then very red stars with all the extinction. Here's a narrowband image, PSF. The same, so catalog PSF, perturbed PSF, and then the fainter target here. So this actually works much better. There's a little bit of an anomalous pixel here. That could be a cosmic ray or something. But this is a 12-point dither, and we would have 36 or 54. So we probably good chance we could get rid of that if it is an outlier. Okay. And in our proposal, we would propose to observe these two events that and two bright source stars to be included in the Keck survey. We use narrowband filters for that. And hopefully, if that works well, then we can propose to observe some more of those. So here's the target list. And also, we've calculated what the, if we don't detect anything, what kind of limits we can get. So for 4 out of our 7 targets, we can detect any host star down to the bottom of the main sequence. All right. So, and then for the other ones, for this event, we can detect down to the bottom of the main sequence if it's in the disk, but not if it's in the bulge. We can't get quite that low. And then these two more giant targets, the limits are more like 0.15 solar masses if it's in the disk. And so MOA events are actually the best for this. And the reason for that is just, as mentioned a little bit earlier, that the MOA high cadence survey started in 2006. And OGLE 3, sorry, the OGLE 4 survey didn't start until 2010. So there's wider separations for the free-floating planet candidates found by MOA. And it's also an unrecognized advantage of the poor seeing at the MOA site because they could get this large field of view with much bigger pixels. And so MOA got a much bigger field of view than OGLE 3, even though they didn't have more pixels on the detector because they could make the pixels larger in the sky. All right. So the remaining difficulties with giant sources are only low magnification events, so hosts possible with smaller separations. This is from the light curve. With a smaller source size, you can get somewhat higher limits on how far the host can be just from the microlensing. You have to long wait for source-host separation when the sources are very bright. Also, the giant source stars have lower level variability is likely. And then super low, well, very low mass planet, free-floating planets could run into problems with bright stars if they have spots. If you just magnify a spot, then it doesn't. The light curve has a shape that you would not model very well with a uniform brightness source or with a uniform temperature source. Okay, so the solution to that is Roman, that we're going to get these finite source effects for much fainter stars, a lot more of them, and fainter stars make it easier to find possible host stars. All right. So
Okay, thank you, Dave. So we've got time for a couple of questions.
Hi, great talk. I was curious if you have considered using kernel photogrammetry for any of these European programs.
Kernel-free interferometry.
Kernel phase
Kernel-free interferometry. We mentioned that in some preliminary discussions. I think the sense was that we didn't think that the review committee would believe it would work.
Well, I mean, it has been demonstrated with the JWST near us, for both, you know, Spain and bright stars.
in crowded fields?
I don't know, well, I mean, it depends on how close you need to resolve something, but you can have a really small, subarray for imaging in order to. I mean, if you have a single source that you're interested in, you can resolve down to like a third of the fraction.
Yeah, I'm not sure that addresses the main problem. I mean, so I mean, what flux ratio can you get at a third of it?
I mean, you're approaching the photon noise limit, you know, the fraction of the.
Well, I mean, we think we're already getting down to the photon noise limit without the net. That we know the PSF well enough that we're getting that. I mean, I don't know. There were a lot of the people on this discussion didn't really understand this method very well, but some of them that did understand it weren't convinced that it would work. So,
Okay, yeah, we can have that.
all right.